So I wrote this presentation for Coppinger's Sunday Supper Club less than a year ago, and I thought, hey, this will be easy. I don't have to change anything. It will be exactly the same. Yeah, that was a dumb idea. So, comments and developments in AI. So, in case you don't know me, Andy Lowe, been torched, we think, for over 10 years. Somewhat, we were trying to figure this out at the table, but I think about a decade. Um, I currently work for MPSCS, which Michigan Public Safety Communication System. I think it's the most important state agency that nobody has ever heard of, because we are the ones who handle communications, walkie-talkies, radios, that sort of stuff there for state police, DNR, MDOT, 911, EMTs, police, fire. We are the ones who handle their radio communications, which I feel like at some point I should probably do a talk on that, because it was very surprising. I had never heard about them until I applied for the job. But before that, 10 years with broadcast engineering at Midwest Communications, WKZO, WZOX, all the AM and FM radio stations, half the AM and FM radio stations in the town here. And I just got to plug it in here. I do a weekly podcast where my friend and I discuss topics about technology, science, video games, all that other stuff there. We can review sort of things there. repodcast.net, but we're actually moving now over to YouTube. That way I don't have to store all this stuff on a server. And when you have 800 plus hour long episodes, that's a lot of storage space. So what is AI? I'm guessing if you all closed your eyes and tried to picture AI, most of you would picture that lovely Hal. Yep. And having a nerdy friend whose name is Dave. That yeah, I get a lot. It's always those fun jokes on there. Me being a child born in the 80s, this was actually my thought of AI. For those who can't see it, that's Whopper from War Games, which was our first introduction, into an AI. Is it benevolent? Is it not? But this is not what AI is. AI, which was actually the Consumer Electronics Show held in Vegas every year in January. The most used word in the press releases at CES this year was actually AI. So it's not as glamorous as HAL or Whopper or anything else like that. Your Google Maps. Google Maps has a machine that figures out the best route for you to take. Or Facebook. People always talk about the social media algorithm. That is basically an idea of AI. There's no humans set it up there, but it's a machine, deciding what you're going to see next on your feed. There's not a human there for every one of us at our Facebook feed. All right, so goal for this talk, which I will try to make it 30 to 40 minutes. Last time I did this was 30 minutes. There's a little bit extra in here, but we're going to talk about a little bit of history because this group loves history. I'm going to talk about Deep Blue and Watson, the chess player and the Jeopardy player. And then I'm going to go into our current generative AIs, chat GPTs, llamas, that sort of thing there. Kind of how they're built. So neural networks, LLMs, transformers, and then we're going to go into diffusion models, which is how the images. So your dollies, your stable diffusions, those type of groups. We're going to go into how those things work. And I'm going to try and stay away from math. I don't know. Do we have our math person here? Are they not this time? I put one equation in here, but there's actually a lot of math, a lot of which I don't understand because I only did intro to calculus. So I'm going to try and stay away from the math, but I think it still works. And then every once in a while, we're going to kind of take a little moment of thought to, kind of just think about things and how the current status and ethics and, privacy and that sort of thing there. So starting off a little bit of history. We all know Deep Blue. This is half of Deep Blue. Deep Blue was basically 2 server racks that IBM put together. Now, does anybody remember the outcome of the 1988 match against Garry Kasparov? Anybody? Deep Blue won? No, Kasparov actually won that match 2-0. And then IBM put some more money into it and decided, hey, let's try and face off against him again in 1996. Does anybody remember that outcome of that match? Deep Blue finally won a game, but Kasparov won the match 4-2. So then once again, IBM put a lot more money into this and asked Garry Kasparov for another rematch, which I think the prize pool was like $500,000 or something like that. So Kasparov's like, okay, I've already beat you twice. Let's go for a third time. So we have the 1997 match, and this is the one where Deep Blue actually won 3.5 games to 2.5 games. How do you draws? Draws are half a point for each team. So yes, it took IBM 3 times to finally beat a match. And of course, as soon as this match went over, Kasparov asked for a rematch. And IBM said, oh, I'm sorry, we've completely disassembled Deep Blue, which, as you can see, that's half of it in a museum in pristine condition. I don't think IBM wanted to press their luck anymore. So Deep Blue, how Deep Blue worked? Brute force. It just took every single possible move that it could take on the board and then tried to figure out every single move that the opponent would make for every single one of its moves, and just kept doing that over and over. It averaged about 8 or 9 moves in there, which, the more times you do that, it's just going to be exponential growth. So is it really intelligent if all it's doing is doing brute force, checking? And how does a machine know what's a good move or not? Well, IBM had about 5 or 6 other chess grandmasters on the payroll as consultants to try and figure out, what's a good. They put all the other grandmasters in a room and said, okay, you guys, we need to make chess a math problem. Like, how much is a pawn worth? How much is a location on the board worth? They had all these other grandmasters come in and figure out the math to beat one guy for the 3rd time in a row. And Kasparov actually requested information from IBM about who the grandmasters were, what chess matches were they looking at for Kasparov, because in chess, you play your opponent. You have an idea of who your opponent's going to be. Kasparov had no idea who IBM was bringing in for this. What matches were they looking at? He was going in blind, and he kept on asking for, any information at all. And IBM said, nope, not going to give you a single thing. We don't have to give you our secrets. Which is kind of funny because during the match, there was actually one move in the 1997 game, in game 2, I think it was move 44, Deep Blue got stuck in a loop. And it couldn't get out. And so there was a fail-safe in there. If it went for so long, it would just randomly pick a move on the board. So there was actually bugs in the system that Kasparov saw this move and he couldn't figure out why the machine did it, because he knew the machine would always pick the best move possible. And it was this random move of a rook. And it a lot of people say it kind of threw him off, because it was completely unexpected. He didn't know what to do with it. And, he says, oh yeah, no, this didn't affect my thing. But after that move happened, that's when the game started to go against Kasparov for the rest of the match. So, moments of thought on this one is openness of information. Trying to figure out how a lot of these AI systems work is a lot of secret sauce. There's a lot of non-disclosure stuff. There's a lot of proprietary information and corporate secrets. We don't really know, how what's the special sauce that makes ChatGPT different than Gemini from Google or Apple's Siri X or whatever they're calling it now? It's it's one of those things where it's like, okay, how do we know these things? These are corporates. They don't want to give up their information because that's what makes them special. And we're kind of just sitting here trying to figure out, okay, how are we going to do this with a black box, right? So let's take a quick look at Watson. We all remember Ken Jennings in 2004 going on his massive streak in Jeopardy. IBM's coming up on the 10-year anniversary of Deep Blue, and they're trying to figure out what can we do. So they think, oh, hey, let's try Jeopardy. It should be easy, right? They make a computer question and answer bot, one of the top 3 in the world, and it gets 35% of the Jeopardy questions right. Only 35%, and it takes minutes for them to do it. So they realize whatever they're doing with this machine is just not working. So they spend millions and millions of dollars, and finally they convince Jeopardy in 2008 to have an exhibition match, and then 2011 Watson beats Jennings and Rudder, and there it is, Watson 77,147. But that's not Watson. That's just a screen with a button attached to it. Watson actually was 10 server racks with 90 total servers. Imagine this whole room filled with server racks. 16 terabytes of RAM, 200 million pages worth of data. They basically tried to grab every single piece of written information that they could and cram it into this computer system. Mainly because they put it in RAM because the hard drives were too slow. They knew they had 6 seconds. They had to get an answer in 6 seconds or it wouldn't matter. So then somebody did the math, 85 kilowatts of power an hour to run Watson, which is, 70 US households. Can you imagine a whole neighborhood run just a game show gimmick? And later, the director of the Watson product said that they had a max success rate of 85%. They could not get Watson because they had all the previous Jeopardy answers and questions and everything, and they just tried to get Watson to get to 100%, but Watson could not get above 85%. And you're imagining 85 kilowatts an hour of them just trying to get that last little bit. So yeah, some moments of thought, the power of AI. I mean, we're talking about climate change as a big thing. We always talk about the Paris Accord and in and out and, trying to keep under 1.5 degrees Celsius. But you're sitting here, Microsoft just bought a reactor at 3 Mile Island. They bought a nuclear reactor that they have, I think it's a 10 or 20-year contract or something like that, where they are the sole recipient of the power of the nuclear reactor. When I looked it up, 800,000 US homes Microsoft wants for their data center. This whole idea of, we're talking about trying to, help out with climate, and suddenly, cryptocurrency and AI I think it's currently at 2% of the global energy input. 2% of the globe is going towards cryptocurrency and AI. And Deep Blue, Watson, both gone. There is a Watson out there called Watson X now, but it is a current generative LLM. They tried to make Watson work. They tried to get it to, do something. And IBM just, they made a gimmick. They tried to put it out in the world, and it just flopped. So here and now, generative AI. So we're talking your Chat GPTs, your Geminis. Is anybody with an iPhone? Is there like an Apple? There's got to be an Apple generative AI. I don't have an iPhone, so I'm not sure. I've always stayed outside of the Apple ecosystem. But any of the, generative AIs is the thing now, and they're all set up as neural networks. So medical people over there, this is for you. First paper was at the University of Illinois College of Medicine, Department of Psychiatry. with the University of Chicago as well. 1943. The brand new neural networks were originally, thought of back in the 40s, but they tried doing this with analog electrical circuits, which you don't have the computational power to handle a lot of very complex things using analog electrical circuits. So the idea was there, they just didn't have the technology to back it up. And then in the 70s, this was actually kind of interesting that I found out. Paul Werbos in 1974, working for the Department of Energy, actually figured out something called backpropagation, which led to a resurgence in neural networks. But at the same time, David Rumelhart in 1985, these guys came up with the same idea, same principle, basic, same math, completely independent of each other. It's one of those things where it's like, the Edison and somebody else coming up, the same thing at the same time. It was very fascinating to see this. The fact that though Paul's letter, came out first, nobody was expecting computer science, breakthroughs coming out of the Department of Energy at the time. So his paper kind of got lost, and most people say that Rumelhart's paper in '85 was the big one that showed up there. And then neural networks kind of fell out of favor in the 90s because other people had found AIs that are not as computational heavy and hard to work with, that, they work okay. So you're talking like your Google Maps, Facebook algorithms. There's a lot of AIs out there that are not as crazy as neural networks. So what changed between the 90s out of favor till now being, the hardware and architecture of choice? Well, graphics cards, computer gaming. Computer gaming is basically the technology where you want games to look good. So graphics cards take, instead of your CPU, which is a single thread, doing a lot of very complex things one at a time, GPUs can do a lot of very simple calculations in parallel. So it's the parallel processing of these things, which led to Bitcoin. Sorry about that. But, the Bitcoin miners figured out that GPUs can be used as calculators rather than just making pretty pictures. And then next thing that happened, data storage. The cost for data storage went down. We all know this. We've all, remember 20 years ago where, 3 gigabytes was a big deal and cost how many hundreds of dollars? And now you can't even buy. I don't even think the smallest flash drive I think I could find was probably 8 gigabytes, 16 gigabytes at Meyer for $5? So data storage dropped off, and these guys showed up with all of the internet and creating information. How much information does Google, Apple, Facebook, Amazon, and Microsoft have? How much data is created on a daily basis on the internet? You have your computational power there, you have ways to store it, and you have tons of new data getting generated every single day. So how do they work? Well, the basis of the neural network is the neuron. It's very simple. Here's your math. One math equation right there. Y equals WX plus B. X is your input value. W is a weight added to the impact value, and then you add the bias, and you get an output value. That's all it is. Very simple thing there. So, example, we all do this, especially those of us going to Europe, converting Celsius to Fahrenheit. I mean, we all do that. Anybody, I got an idea of what, so we got 20 degrees Celsius. Anybody have an idea of what the weight would be? And remember what the math, 9/5 or 1.8 for those of us who are not doing fractions. And then what do you do after that? Add 32. So there you go. You have 20 times 1.8 plus 32 gets you 68. So there we go. We've got a neuron that will convert Celsius to Fahrenheit. That's all it can do, though. It can't do anything else. But there doesn't have to be a single input for a neuron. So you could have multiple inputs and a bias, and then that neuron could also have multiple outputs. Therefore, we get the neural network. And note, for math, for some reason, didn't really get into this, but the neuron outputs are adjusted between 0 and 1. I think computer science people really love binary. So 0 means, 0, and 1 is 100%. But that's just a side little note there. So here we go. There is a neural network. This was done by 3 Blue 1 Brown, which, let me tell you, if you are very curious about computer science stuff, there's just tons of good information out on YouTube. Just the amount of people out there who want to help other people understand and learn without even dropping well, I'm watching the YouTube ads, so I'm technically paying with my time. But it didn't cost me anything, and there are a lot of people who are explaining the same topic in many different ways. So this is a neural network that he created, has 784 neurons in the input layer, and then those are all connected to 16 neurons in the one middle layer, and then there's a second middle layer that also has 16 neurons, and then you have your output of 9 neurons, or sorry, it should actually be 10. I miscounted. It should be 10 actually neurons in the output layer. Sorry, my bad on that one. So you have 13,002 total weights and biases. That's it, just 13,000, which for a neural network is actually very manageable. He actually did this he created this specific design just because it looked good on YouTube. It was the only reason why he picked 16, 16, and your 10 digits at the end. So what he did was, for the inputs, he did pixels. So individual little pixels are either on or off. That's why there's 784 input layers. So each one of those pixels is either on or off if there's, something written there. And he was doing this just to try and figure out how it works. And to think about this guy spun this up for a YouTube video. Spun it up in an afternoon, let it run for about a week or so. So, we always talk about like guardrails and, having the, Chat GPT not telling you how to make a bomb or anything else like that. Well, those are the big players, but you can spin up an AI without much work at all. He did this on a whim, and if I remember correctly, he got about an 80 to 85% accuracy for recognizing numbers. And some of the professional optical character recognition ones for that data set there were, I think, 87 or 88%. So he did this on a whim just to make it look good. And he made something that almost worked as good as the top tier AI stuff there. So, we always talk about, Chat GPT won't help you with this or won't help you with that. But there are people out there who can make their own, and they don't care if they're, doing something illegal or not. So, think about, yes, people are going to, talk about privacy and ethics, but this is something you can do in your own home. So the first step is this. Yeah, it doesn't look as clean and precise as previous one. As you can see in the 10 digits at the end there, there's a lot of gobbledygook. So very beginning, you have random weights and biases. You just tell the computer, pick a number for a weight and a bias, and then you feed it a known data set, and then you just kind of let it do its thing. So it will give you just bad answers. It will give you any answers, and you kind of just compare the output to the expected output, and that is what in the industry calls the cost. The lower the cost, the better your AI is. The higher the cost, the worse your AI is, and the more, the farther it is away from other answers. And moment of thought here, data sets. We talked about, Amazon, Instagram, Facebook, Google, all these people generating data all the time. But, some of these other people had to get data from somewhere. And a lot of this guy pulled his number data set of known values. Does anybody want to take a guess where he pulled a huge amount of numbers, handwritten numbers? US Census data. because there are addresses and ages and birth dates and everything. So there is a huge optical character recognition data set out there that is entirely based off of open, government data there. And then the Watson people, they didn't actually have to get a data set of previous Jeopardy answers, because it turns out there was actually a Jeopardy fan club out there that was actually diligently cataloging all of the Jeopardy questions and answers that they just went and pulled that data from without even having to do it, without actually really even thanking the fan club for the amount of effort and time that they've had to put in on this. So, data is coming from everywhere. It's like your Instagram posts are data, your Amazon purchases are data, Facebook posts are data, everything. People are using these things without your knowledge that, using the data to train AI. And the question is like, people are like, well, isn't this illegal? Well, it's not illegal because nobody expected they needed to write a law for it, It's like, if I suddenly started firing a ray gun, it wouldn't be illegal because nobody thought a ray gun would exist. Nobody has created a law for ray guns. So, it's not illegal until somebody says it's illegal. And we're kind of behind the ball on that one because hate to say that the horses are already out of the barn. The data sets are already out there. There are a lot of authors now who are actually poisoning. They're putting poison pills in their online information to try and stop, automatic scrapers and automatic registers of everything. People are putting stuff in there to try and trick the AI into, not accepting their data, or if they do take their data, having the data spoil the data set. So, okay, so how do we go from this craziness to something a lot smoother? Very beginning, last one there is the very end. So we got to train our neural network. And the goal is to lower the cost. And the best way to do that is back propagation. Here we go. This is those two guys back in the 70s and 80s. Back propagation, very complex math. I don't want to go into it, but the idea is you increase the weights and biases, feeding the correct output neuron, and decrease the weights and biases of the neurons, feeding the wrong output neurons. And then you increase the weights and biases of those, decreasing the weights and biases, feeding the other ones. And then you increase the weights and biases, feeding those, and decrease the weights and biases, feeding the other ones. And the words of King and I, etc., etc., etc. You just work all your way from the very end, work your way all the way to the beginning, and you get this. So the idea would be, this was a neural network that came with the output of the number 9. So you would take the neurons in the previous layer, those that correctly fed 9, as you can see those 2 of them there at the top. You would increase the weights and biases of those, and then you would decrease the weights and biases of all the other ones, the other 14 on that layer. And then you would go back, the layer before that, and you would take all the ones that are feeding those 2 in the middle layer, and you would increase the weights and biases of those, and then all the ones feeding all the rest of them, you would decrease the weights and biases of that. Does that make sense for people? You increase the good, decrease the bad, and you just work all the way back to the beginning, and then you run it again and again and again, doing that over and over and over until you're happy. There's a lot of times where there's an acceptable cost for your LLMs and your other neural networks that, people just, you can't get it 100%, but you'll get it at some point. You'll get to that, it'll start to drag off, so you accept it. So then neural networks, now we get to the LLMs. LLMs stand for large language models. So a language model is a text predictor. Your cell phone has a language model. That little bar right above the keyboard that suggests, your next word, that's a language model. It's not a great one, but it for what it does, it works, right? It works most of the time. Well, that's why they give you three options normally. It gets close. It's a language model. It's not a large one, because large means that you basically have every piece of written work available as an input there, as we talk about data, 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 and then the parameters. Some LLM networks have trillions. We are up to the trillions level now of weights and biases. So that, like I said, that neural network, 13,000, that's you could make an Excel spreadsheet out of that. You can't make an Excel spreadsheet of trillions of weights and biases. So LLMs, massively complex neural networks, taking massively large amounts of data in order to predict the next word. That's what LLM they all they do is predict the next word. So training an LLM, it's a little bit different. So words are broken down into numbers and they're called tokens. Now numbers are actually in this I put numbers in quotation marks, but I'm actually talking about is vectors. Do we have any linear algebra folk in here? What? But any linear algebra? Linear algebra? You're a masochist, is what you are. Tried to understand linear algebra, not going to do it. So, for those of us who don't want to feel pain, I've kind of broken it down. So, we'll just take the number 13. All right. Well, 13 is a number, but we can kind of describe it multiple ways. We can say, oh, it's a number that's greater than zero. It's an odd number. It's a two-digit number. It's a prime number. So you can actually make a list of information about 13, and that would be your number. So it has lots of individual variables that you could describe that. That's what they do when they tokenize something is they take the math on multiple dimensions and basically have different number values for everything. And OpenAI, for theirs, they found the sweet spot to be about 1,536 variables for each token. Which you could have higher ones. There are some out there that have I think about 4,000 variables for each token, but then the math becomes a lot more complex. Multiplying 1,000 numbers is hard, but then multiplying 4,000 by another 4,000, you get a lot of calculations. So OpenAI kind of put theirs right around 1536. So let's talk about training an LLM. Self-supervised training. No humans involved at this point, basically. The model takes a known string of tokens, or we could call it a sentence, and omits the last token, or we could call it a word. So example would be, the sky is blank. So this is a sentence that it pulled from the data set somewhere that has an answer. So it could be the sky is clear, the sky is blue, the sky is cloudy, something, but it knows, it's a known sentence. It just chops off the end and tries, it runs it through and tries to guess what the word is. So yeah, so it tries to predict the last token, and if it gets it right, great. If it doesn't get it right, adjust and try again. And this is kind of where, has anybody heard of hallucinations with AI before? This is kind of where the hallucinations come in. So my best example is, we all know about ISBNs. Anybody ISBNs, the International Standard Book Number? Yep. So when Amazon, is doing a training on their own data, Amazon sells books. Every book has an ISBN number. So you feed that into the system and you say, okay, the neural network at some point will hit ISBN and it will know that there has to be 13 digits after that. That's the length of an ISBN number. But it just knows there has to be 13. It's got a huge list of 13-digit, numbers. So how do we know that the 13-digit number it picked is an actual ISBN number, or could just be 13 random numbers that it picked out? Does that make sense? It's one of those things where, yeah, you look at it and you go, okay, ISBN, 13-digit numbers. You don't, the machine says, here we go, here's an ISBN number. Well, there's not, you would have to actually look at it and, research and check to see, is this an actual ISBN number, or is this a hallucination that the AI created in order to answer your question? And what's really funny is researchers at Google in 2023 tried to figure out on their LLM how it knew facts. So they asked it, I think the prompt was something along the lines of like, fact, Michael Jordan plays blank. They just like, Michael Jordan plays, and they stopped it because it predicts the next token, right? So they were trying to see that the LLM would actually predict basketball, and they were trying to figure out where in the massively complex neural network basketball is, where is the memory stored that it knows the fact that Michael Jordan plays basketball, and they couldn't find it. They had some good guesses. They had some, they had plenty of hypotheses, but they didn't, in their paper, they specifically stated, we don't know for sure where this information is being stored. Yeah, it did predict basketball, but they don't know where in the system that it shows up. Where in this massively complicated, multi-layered, thing is basketball? Michael Jordan plays basketball. Somehow it knew that, but they don't know how it knew that. And this is like Google researchers taking their own, artificial intelligence and trying to figure out how it works and failing at it. So, okay, some more training. Now we get to the human factor of it. Reinforcement learning from human feedback. So sometimes you would have a human expert answer example prompts, and then the AI would learn that, okay, this is, I want to try and be like this expert. So it's going to learn, what an expert thinks of your prompt. But then, the model outputs are adjusted so its outputs are similar. Good one here was actually translating between languages. So you would have, you would put something in there, and you would have a person who is fluent, tell you what the actual, translation is, and then the machine would learn, okay, this is what it's supposed to be. And then actually most now actually go a step further, where the machine will give multiple outputs, and then a human would rank them from best to worst. And then those rankings would be used to train another AI, which would then read the outputs of the AI and use that to say, okay, this is good, this is bad, this is good, this is bad. So this is kind of the flow chart of it. So you have your prompts in the lower left corner here. They're fed into one model. There's a sampling sent out to the humans. The humans rank them, use that to train the reward model. And then that kind of, works on the aligned model. And then it starts to cycle between just the blue. The humans go in one time, give a ranking, and then they just send it to machines because time is money, and the machines can do this a lot faster than we can. As soon as we put humans in the loop, things slow down to a crawl. Which, yeah, great. All right, so original LLMs were called recurrent neural networks. Tokens were done sequentially. So each previous prediction, you did the math, you came up to a total, and then you went to the next token, and you did that total plus the latest token, come up with a new one. So example, say you have a string that's 1, 2, 3, 4. So you would start out, 1 plus 2 is 3. Okay, so you would have that answer, and then you would take the next token. So you have the previous answer plus the next token, and you get an answer of 6. And then you take that answer plus the next token, and you get 10, and so on and so forth. So you would always add up one more token, do the math, add that up, get a total, and then go to the next token. This was extremely slow, but that was what people had at the time. You know, it was just the way it worked. It worked somewhat. It was slow, and there was also memory loss. So, how many people know the Groucho Marx line? I got up one morning and shot an elephant in my pajamas. Yeah, how he got in my pajamas, I don't never know. Um, so it would just take this and would go, okay, I plus got gets me a number, plus up gets me a number, that number plus one gets me something, and so on and so forth. So I actually found an AI image generator that I knew was a recurrent neural network, and I gave it the line, and this is what it gave me. And as you can see, it put the weight on my pajamas on the elephant rather than me, because the elephant happened later in the sentence. So it was fresher in the AI's mind rather than the I at the very beginning. It's like making a photocopy of a photocopy of a photocopy of a photocopy. Sooner or later, that original one right there at the very beginning, you know, gets lost. Well, that's what it was one of those things where, yeah, no, the AI may or may not have gotten the joke, but it definitely knew that it was not me in the pajamas. It thought the elephant, being later in the sentence, must be wearing the pajamas. And then we hit transformers. This is the T part of GPT. The G, generative, P is pre-trained, as we talked about with all the training. And then we hit the T, the transformer. It's literally 2017. Attention is all you need. This was the watershed moment for generative AI. There's no ifs, ands, or buts about it. This paper was the changing point for AI. There were, as of last year, I actually looked this up. This paper has been cited more than 140,000 times. So this was the paper that took everything and flipped it on its head. 8 scientists at Google were the ones who authored this paper. And I'm just going to leave this fact out there. 6 of those 8 authors were born outside of the United States. The other 2, one was a child of green card carrying Germans who were temporarily in California. And the other one, the last one, was a first generation American whose family had fled to our country to leave persecution. I'm just going to leave that out there with our current political landscape. Just leave it right there. So these were originally for use with actually Google Translate. As we had talked about, you kind of need an expert in, a language to understand all the nuances and everything, because, the language might not be left to right. You might not be able to do it one word at a time. You need somebody to actually understand the nuances and connections. And so parallelism is what showed up. As we talked about, that GPU being able to do a lot of calculations in parallel, the transformers were able to still use tokens and neural networks. So you didn't have to worry about the architecture, the basic architecture changing. All you did, though, was embed word position and word relationship into the token. And so it was really hard to find a good visual for this, but this is the best one that I could find. So there's a text sentence going from top to bottom, and you can see the little bars going across that kind of show the relationship of the word to the other words in the sentence. So when it would do, instead of going, 1, 2, 3, 4, 5, 6, it would actually, when you're doing pre-training and tokenizing and everything, all this stuff would be relationship of word position and word relationships to other words. And it would do all the math in one go at the same time. And computer science people love doing things in parallel because then it cuts down on time. And you can do a lot more calculation. So this, Transformers in 2017 came out, flipped AI on its head a bit. And then after that, 2022, talking Chat GPT comes out. GPT-3 actually at the time. And everything just goes off from there. Oh, geez, I'm already at 15 minutes. Shoot. All right. What's possible? Computer vision. We're talking about imaging stuff. Computers can recognize an image where it's located and describe it to you. This is already stuff that computers can do. Noise reduction. Computers can take a grainy image, make it smoother. So diffusion models, we're going to take text, make an image out of it. So training process for that, no text. We're going to train a model to take text and turn it into a picture. We're not going to start with text. We're going to have a forward process and a reverse process. So forward process, you add a little bit of noise to an image, and you tell the computer to guess how much noise is on there. Because the computer can already tell what's noisy and what's not noisy. And it will, model tries to predict the amount of noise and then adjust the neural network, etc. So here it is, picture of a rhino. It just adds a little bit of noise, calls that, a learning model, and then adds a little bit more, and then a little bit more, and a little more. So this would be 5 different training pictures from just the one. And you would tell the neural network to try and figure out how much noise and what the noise is in each picture. All right, so that you're training an AI to recognize noise and recognize an image, and how to get rid of the noise, which is the reverse process here. So this would actually start down here at the bottom with a noisy picture. You tell it, hey, remove some noise, and it would just do it one step at a time. So it would remove some noise, and you would compare it to the next one, and then it would do it again. And as you can see, after a couple of times, you start to get a picture of the pyramids there from the noise. So you're teaching an AI to take a noisy image of some kind or just noise and create an image out of it. So you had to go through the process of teaching it what's noise, what's picture, and then you just give it a whole bunch of noise and you turn it back into a picture. So, all right. Images created from random noise. Random noises could just be random numbers, which could be, a string of tokens. A whole bunch of numbers in a line kind of look like random numbers. So you would, some actually use the same tokens as LLMs. So you take a known prompt, turn it into a string of numbers, run it through the machine that will take this random noise of numbers and turn it into a picture. And then you run it through the caption generator and see what came out at the end. And then results are compared and you put it together. Does that make sense? I went a little rushed, but yeah, we're running out of time here. Yep. Yeah, so this one here was a text prompt for a feudal castle or a feudal Japanese castle in Germany. And as you can see, it starts out just, it takes the text prompt, creates noise from your numbers, because noise and numbers are the same thing. And then each time removes a little bit of noise, compares it back to there, and then goes another step and compares it back to your, prompt. And then after about 40 steps, you actually got a pretty decent looking feudal Japanese German castle. Yep. Okay, so then other generative AI types, we're talking about video generation. Videos are just a sequence of pictures. So if you have an AI that can create pictures, you put enough pictures together, you get a video. Sora actually it came out right before I did the last presentation. Sora actually is able to do transformers. So it's actually able to do image generation in parallel. It's a whole time-space thing there. It was very confusing to try and learn about. Audio generation, text-to-speech. We all know about Siri and Alexa and everything. Well, Microsoft released a program called Valley in 2023. Only needs 3 seconds of audio to mimic a voice. Just 3 seconds of audio. And of course, it could potentially see the words placed into the mouths of a politician, actor, or even a family member asking for money, which have all happened. Does anyone remember the Joe Biden robocall that wasn't actually Joe Biden? Yep, came out after this. And then, yeah, computer code. Computer code is codes are just another language. So GitHub, which is owned by Microsoft, released in 2021, it can read, write, and modify code on the website as an AI. And then thing that just came out, DeepSeek, the one that blew a whole bunch of market cap off of NVIDIA, was actually created by a Chinese hedge fund lab, which you bet they probably shorted some NVIDIA stock before making their public announcement. Yeah, 5.6 million total cost of hardware and training. And we're talking normally like the open AIs and everybody else here are in the billions and trillions. And the surprising fact was there is actually a current ban on current AI hardware getting sold to China. Oh, did I? Oh, 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 I broke it. I broke it. Yep, I hit the wrong button. Yeah, I said China, and then they came for me. But yeah, so the U.S. is currently banning sales of the top of the line AI hardware to China. So it was basically best example I had was we've got Ferrari and Lamborghini over here. Somebody in China took a box of used Chevy parts and built themselves a Ferrari. Oh, could be something like that. So the other thing here with DeepSeek is it uses mixture of experts, so it doesn't actually go through the whole neural network. They actually have segmented the neural network depending on what kind of question you ask. So it does that was helpful of the thing there. And then OpenAI actually accused them of distillation, which means they had DeepSeek pulling answers from OpenAI and then training itself to mimic those answers. So DeepSeek might not actually be smart, it might just be a parrot. You know, it can speak, you know, it knows what answer OpenAI gave, and it's trying to mimic that same answer for itself. Yeah, it could be a deep fake. And I just want to leave you on this here. Right now is the worst that this AI can be. It was somebody said this after Sora came out because Sora was it was surprising. Sora was a big leap in video AI generation. And somebody was like, just think about this. This is the worst that this AI can be. It will only get better in the future. All right. So yeah, sorry about that. That was a little long, my bad. But